Today, we are going to start the second part of this course, which is dynamics. Today, we are going to have introduction about the dynamics, and also we are going to talk about the rectilinear kinematics, and we are going to talk about the continuous motion. So remember the mechanics in the first lecture in this course. We talked about the mechanics, and we say that the mechanics is the study of how bodies react to forces acting on them. So the purpose of mechanics, we know that in nature, the bodies is going to be subjected to forces, especially if I'm going to build something, whether it's car, machine, building, etc. They are going to be subjected to forces. So we need to know how to handle those forces. And this is the mechanics. And the mechanics, it could be for rigid body. We are going to assume that we don't have any deformation. And also it could be for formable bodies, deformable bodies. And in that case, the bodies, they are going to deform because of the forces. And also we have the fluid mechanics. In that case, we are not dealing with solid materials. We are dealing with gases or liquids. In mechanics, in this course, we are concerned with the rigid bodies. In the rigid bodies, we don't have any deformation. And in the rigid bodies, we have the statics, which is the study of bodies in equilibrium. The body should be in equilibrium. So that means the body is not going to move. And in that case, we are going to use the Newton's first law, which is the summation of the forces acting on that body should equal 0. The second part, which is the dynamics, we have two categories. We have kinematics and we have kinetics. In kinematics, we are going to study the geometric aspect of the motion. In this case, we have a body, and that body is going to move. And if that body is going to move, it means that it's going to have a path to move. And in this path, we are going to study the position for that particle and the velocity, since now the body is going to move, and the acceleration, and of course, the time. The second category in dynamics, which is kinetics, this one concerned on the forces causing the motion. And in dynamics, we are going to use the Newton's second law. The forces acting on the body is going to be the equal the acceleration, the mass times the acceleration. Not like here. The forces should equal 0. Here, the forces should equal the mass times the acceleration. So we are going to start with kinematics today. And to be exact, we are going to talk about rectilinear kinematics. In rectilinear kinematics, the motion is going to be along a straight line path. So rectilinear motion, it means that the particle is going to move along a straight line. Because also we have curvilinear motion. In curvilinear motion, the particle is going to move along a curve. So here we have the simplest case. The particle is going to move along a straight line. And in kinematics, like I said, we need to specify the particle's position and the particle's velocity and the particle's acceleration at any given instant. So we need to know the position when the time is 0, also for the velocity and the acceleration. Also when the time is 1, we need to know the position, velocity, and acceleration, and so on. At any given instance, we need to know the position, the velocity, and the acceleration. So we're going to start with the position. What does it mean by position? So assume I have a particle here. In order to deal with that particle, to know the position of that particle, we are going to set up a single coordinate axis S. So here we are going to have only one coordinate system here, single coordinate axis. We are going to call it S. So if I have a particle here, I'm going to install a coordinate, single coordinate system S like that. the particle is going to move along that axis S. That is why here we said we have rectilinear kinematics. We are going to study the motion of the particle along straight line path. So that particle is going to move only along that line. This direction is going to be positive, and of course this direction is going to be negative. And the position of that particle here is going to be measured from the origin. So here the point O is a fixed point, and it's the origin for the motion. So from O to the particle, here represents the position of the particle. Also, we have the displacement. In the displacement, the particle, now assume the particle is at that location. Then the particle is going to move from that location to that location. So the difference between the first position and the final position, we are going to call it the displacement. So displacement equals the final position x hat minus the initial position s. This represents the displacement, delta s. So s is the position, and delta s is the displacement. Also, we need to understand the velocity. The velocity is a measure of the rate of change in a position of a particle. So we need to know if, again, if I'm going to have a particle here, and the initial location was here, and the final location was there. Now the particle is going to change its location from here to there. So the velocity is a measure of the rate of change. So we want to know how that particle is going to move. We need to know the rate. Okay, so in this case, the velocity is the measure of the rate of the change in the position of a particle, and it's the vector quantity. The velocity of a particle, it has magnitude and it has direction. So here in rectilinear, the direction is here. So the particle is going to have velocity from here to here. The magnitude of the velocity, we call that the speed. The speed is the magnitude of the velocity. So if in order to define the velocity, I need to know the direction and I need to know the magnitude. That is why it's the vector quantity. So here we have the average velocity. So if I have a particle moved from here to here, and I need to know the average velocity for that interval. So assume the time here is 2 and the time there is 4. And I know the position for the initial location and for the final location. In that case, if I want to know the average velocity, it's going to be the difference or the displacement here over the time interval, the time from here to here. And we define this as the average velocity. So if I'm going to have a particle, initially it was here and then move there, I'm able to determine the average velocity by determining the displacement, and I'm going to divide it by the time interval, the time from here to there. Also, I can determine the instantaneous velocity. I need to know the velocity at a very small change. If that value, delta S and delta T, it was very, very small. We need to know how to express the velocity. And that it could be defined as the limit of delta S over delta T when the delta T is almost 0 here. And from math, we know this, it could be expressed as V equals ds over dt. We call this instantaneous velocity. That helps us to determine the small change in the position with respect to the time. So we have the average velocity, and also we have the instantaneous velocity. The velocity, it could be positive. If it's positive, Remember the single coordinate system. If it's positive, that means the particle is moving to the right. And of course, if it's negative, that means the particle is going to move to the left. So the velocity could be positive or it could be negative. We said that the speed is the magnitude of the velocity. And of course, the speed cannot be negative. And if you are going to determine the average speed equal the total distance traveled over the elapsed time. How that is possible? Assume the particle was here at P. Then the particle move at that point and then get back to that point. So P is the initial position. P hat is the final position. So for that particle to move from here to here, the total time was that time plus that time plus that time. So here is the total distance traveled. So that particle traveled that distance and then that distance and that distance. But if you are going to determine the displacement, the displacement is going to be only this value. So displacement is this value only, and the total distance travel is going to be from here to there. We are going to measure the total distance travel, not the displacement. Not the displacement. We have a difference between the total distance traveled and the displacement. If you are going to determine the average speed, is going to be ST, the total distance traveled over the elapsed time, delta T. And that is the difference between the average speed and the average velocity. Remember, we defined the average velocity in the beginning of this lecture, or in the previous slide. We said that the average velocity is delta S over delta T. Delta S is the displacement. And here we have the ST, the total distance traveled. To understand that, I'm going to show you this example here. We have a particle. So that particle moved like 5 meters and then get back 5 meters. So now the total distance traveled is 5 plus 5, which means that the total ST is 10 meters. Then what about the displacement? Here is the initial position, and here also is the final position. It means that the delta S now is 0. So if I'm going to determine the average velocity, it's going to be delta S over T. Delta S in this case is 0. It means that the value of the average velocity is going to be 0 as well. But in case of average velocity, we are going to determine the total distance traveled. And in this case, is 5 plus 5. And the average velocity came out to be 2 meters per second. So we need to differentiate between the average velocity and the average speed. Finally, we have the acceleration. We said that we need to study the position, the velocity, and the acceleration. We call this kinematics. And regarding the velocity, again, here we have the initial position, and here we have the final position. This particle here is moving with a certain velocity. We are going to say this is the initial velocity, and the particle here now in the new position is moving with a new velocity. So here I have velocity at the initial location and velocity at the final location. Then if I'm going to determine the average acceleration for that particle from this point to that point is going to be the change in the velocity, which means that V hat minus V over the interval time, the time from here to there, the difference in time. So the average velocity is the delta V over delta T. And again, I can determine the instantaneous acceleration. I need to determine the velocity after a very short time here. And that could be found by taking a smaller and a smaller value of delta t. So we are going to use the average speed in order to determine the instantaneous acceleration. In that case, we are going to say that the instantaneous acceleration is the limit when delta t is going to be 0, delta v over delta t. And we know that from the math, from the calculus, that value is the dv over dt. So in order to determine the instantaneous acceleration, the value is going to be delta v over delta t. And remember, we define v, the instantaneous velocity, we say that is the ds over dt. So also I could say that the instantaneous acceleration is the second derivative of the position with respect to time. Okay, so I could express it like that if I know the velocity, or if I know the position, I could express it like that. The beauty about this equation, I'm going to use the calculus in order to move, or if I'm going to have, for example, the equation for the position, I'm going to be able to know the equation for the velocity and the equation of the acceleration. Is the beauty about the calculus. It's going to help us to know the acceleration at any given distance. So using those equations, I'll be able to know the position and the velocity and acceleration at any given time. So also the acceleration could be positive. That means the speed is increasing. Or it could be negative. That means the speed is decreasing. So in this case here, we have acceleration. That means the speed here is increasing. V hat here is more than V initial. Or it could be negative. That means the speed is decreasing. That means the value of the final speed is less than the initial speed. In that case, I have deceleration. So to summarize all of this, to summarize those important equations here, we said that the velocity is the first derivative of the position with respect to the time, ds over dt, and the acceleration is the first derivative of the velocity with respect to the time, dv over dt. Now we can get a third equation out of equation 1 and equation 2. Here I can put dt there. I will be able to solve for dt. In that case, dt is going to be ds over v. Here also I have dt, so dt is dv over dA. That means this quantity is going to be the same as that quantity. So dt from this equation is ds over dv, and from that equation, dt is the dv over a. So this quantity equals that quantity. So I'm going to rearrange this equation here. I'm going to end up with a ds equal v dv. Like you can see here, this equation is this equation here depends on the time. Also, this equation depends on the time, while this equation does not depend on the time. So now let's solve examples so that we can apply what we have discussed here. So in example 1, we have a particle moves along a straight line. You see here, it's move along a straight line. That means I can use the rectilinear equation that we have discussed right now here. And they say that the position of that particle is going to be defined by this equation. So I have a particle moving along a straight line. And in order to know the movement or the position of that particle, we have equation for that. The position equal t cubed minus 12t squared plus 36t minus 20 centimeter. So this equation is going to give us the position at any instant. For example, if the time is 0, I'm going to put 0 here instead of the t, and the position is going to be -20. So when the time is 0, the particle was on -20, which means that I have 20 centimeter left to our single coordinate system. So using this equation, we can describe the position of that particle. And also we need to know interval time. So he says that the interval time between 0 and 9. And he wants to describe the motion of that particle during that interval time. To describe the motion, I need to know the position, and also I need to know the velocity, and I need to know the acceleration. Here I have only the position. In order to get the velocity, we need to use the equations that we have discussed today. We say that here is the equation to describe the position. I'm going to say that we learn the velocity is ds over dt. So I'm going to use the calculus in order to get the formula for the velocity through the formula of the position. Also, I could get the acceleration because the acceleration is dv over dt. So using the equation of the position, I'll be able to know the equation for the velocity and the equation for the acceleration. And if I'm going to know those equations, if I know the time interval, I'll be able to describe the motion. So we said that the velocity is ds over dt, which means that I need to differentiate this formula here. So using the calculus, here we have t cubed is going to be 32 squared, and this one here is going to be 24t, and this one is going to be 33, and this differentiation of this constant is 0. I can simplify that problem, that equation, and it's going to be like that. Similarly, I can get the value of the acceleration, because the acceleration is dv over dt. I'm going to differentiate that equation here. It's going to be 2t minus 24. Also, I can simplify it like that. Now I know the time interval. If I know the time interval, I'll be able to describe the motion. So I'm going to put that table here. The time is going to be 0, 2, 4, 6, 9. Also, I can say that 0, 1, 2, 3, 4, but the table is going to be too long. So I'm going to put it only 0, 2, 4, 6, 9. In order to describe the position, I'm going to substitute 0 in that equation. And here, like you can see, it's minus 20. Then I'm going to substitute 2 here. And the position, like you can see here, and so on, until 9. So when the time is 0, the position was minus 20. When the time is 9 seconds, like you can see here, the position was 61 centimeter. Then also, I can describe the velocity. Here I have the equation for the velocity. I'm going to substitute the value of t. If the value of t is 0, the velocity is going to be 36. So when the time is 0, the velocity was 36. When the time is 9, the velocity was 63. Also, similarly, I can do that for the acceleration. Here I have the equation of the acceleration. I'm going to know the acceleration when the time is 0 and when the time is 9. Now also I can determine the other factors. Like I can determine the speed, the average speed, and the average velocity. Here is the line represents the motions. So at the first location, it was here at minus 20 when the time is 0. Then when the time is 2, it became 12. So from minus 20, it moved to plus 12. Then when the time is 4, it became minus 4. So it moved here. When the time is 6, it became minus 20 again. Then when the time is 9, the position became 61. Then it's moved positive like that. Also, like I said, I can know the total time. The total time is 9 seconds because 9 minus 0. The total distance is going to be the distance here plus there plus there. The distance here is minus 20 minus 12. Of course, the distance here is going to be positive, which is 32. Also, if I want to know the distance here, it's going to be 12 minus 4, which is 16. Also here, until I get to the last point. Okay, so here I can know the total distance traveled. Also, the displacement, like I say, that the displacement is going to be minus 20 and 61, which is 81. So the difference between this point and that point, while the time travel is all of this distance, the difference between the total distance and the displacement. Also, I can determine the average velocity. I can determine the average velocity, this value here, and that value here over the 9 delta V. Okay, and here I have the average speed. We say that the average speed is going to be st over the time. The average velocity is the displacement over the time, like you can see here, and the average speed is st over delta t. This is the difference between the average velocity and the average speed. In the average velocity, we are going to use the displacement. In the average speed, we are going to use the total distance traveled. And also, we can determine the average acceleration, the difference between the final velocity and the initial velocity over the time. So now we can determine or describe the motion of that particle. And also, we reviewed all the concepts that we have discussed here in this lecture. Also, we can solve another example. Here we have that car. The car on the left in that photo here, in this figure, move in a straight line. Since it's move in a straight line, we can use the rectilinear equations. And for a short distance, a short time, its velocity is defined by that formula. So here he gave us a formula to describe the velocity. And like you can see here, the velocity is a function of the time. So if I know a specific time, I'll be able to know the value of the velocity. So where t is in seconds. So the value of t here is in seconds, and here is foot per second. They want to determine its position. We need to know the position and the acceleration when the time is 3 seconds. When the time is 3 seconds, we need to know the position of that car and the acceleration of that car. And also he said that when the time is 0, so when the time was 0, the position was 0 as well. So in order to solve this problem, first we need to set up our single coordinate system S. So we are going to put only one coordinate system S. In that system, the velocity is going to move, the car is going to move along that single axis. In that direction, we have the velocity and we have the acceleration. So how we are going to solve that problem? First, we need to set up the coordinate system. Like we said that the position coordinate system extends from the fixed point O to the car. The positive is here. So here is our coordinate system. Then the expression for the velocity was given. So through that expression, I can know the velocity at any given time. And in the first part, we need to know the position. So here we have equation 1, 2, 3. Those are the most important 3 equations. Through that equations, I'll be able to get expression for the position and for the velocity and for the acceleration. Now I need to determine the position. In order to determine the position, I need to use one of those equations. So which one is it? Either to use the first one, the second one, or the third one. So I need to get the position. Here I have ds. And in order to get the position, I need to integrate dt. The equation depends on the time, and v. And here I have the equation of v. So the most suitable one is this equation here. So in order to get the position, I'm going to use this equation. And as we can see that the velocity is a function of the time. So I'm going to use this equation. So v equals ds over dt. And here is the equation of the v, the velocity. Then I'm going to solve for ds. The ds is going to be this equation times ds. ds is very, very small. In order to get the position, I need to integrate this part and that part. So I'm going to integrate this part and that part. Now, how I'm going to know the integration limits? Remember, he said that when the time is 0, the displacement also is 0. So we are going to start from 0 to s and from 0 to t. So integrate this part, are going to have s, and integration of that part, we are going to have t cubed plus 2 plus t squared from 0 to t. Then I'm going to have that s equal t cubed plus t squared. So now I need to have expression for the displacement. And through that equation, I'll be able to know the position of the car if I know the time. So in the question, he said that he want to know the velocity when the time is 3. So I'm going to substitute 3 here in that equation to determine the value of the position. The position came out to be 36 feet. So when the time is 3 seconds, the position of the car was about 36 feet from the origin. Oh. Of course, using this formula, I can know the position at any given time, not only 3 seconds. If I want to know the position at any time using this equation, I'll be able to know the position. The second part, also I need to know the acceleration when the time is 3 seconds. So this time also I need to think about those 3 equations. I need to know the acceleration. So in equation number 2, I have acceleration, I have time, and I have velocity. So this one is the most suitable one. So I'm going to choose this equation. So I'm going to say that the acceleration A equals dv over dt. Instead of v, I'm going to put the equation here like that. And then the acceleration is a differentiation for that part. So I'm going to differentiate with respect to dt. So the differentiation of this one here is going to be 6t plus 2. Now I have expression for the acceleration. And in order to know the acceleration when the time is 3, then I'm going to substitute 3 in that equation, and the acceleration came out to be 20 foot per second squared. And it's positive, that means the acceleration is increasing. Okay, I'm going to highlight the